My name is George Hope Chidziwisano. I am a PhD student in Information and Media at Michigan State University. This presentation is about our research on exploring the role of sensor-based technologies in Kenyan homes. Like in other developing countries, power blackouts are a common occurrence in Kenyan households. Every year, an average household experiences at least 700 hours of blackouts. In fact, the World Bank gave a score of 0 out of 8 to the Kenyan electricity supply company. Power blackouts have so many negative impacts on everyday activities of people. These include damage of electric appliances, increase in crime rates, income generating activities. These challenges affect end users of electricity in Kenyan households. Now researchers have used sensors to collect power blackout information and send it to companies. It is not clear how this information can support end users' everyday lives. Providing real-time information about power blackouts can be essential for protecting appliances, saving time, as well as improving income-generating activities. We explored how sensor-based technologies can be used to monitor power blackouts in Kenyan households. We were guided by the following research questions. How can sensor-based technologies support power blackout monitoring in Kenyan households? What are the implications of using sensor-based technologies to monitor power usage in Kenyan households? To answer these questions, we designed GridAlert, a sensor-based technology that detects power status in households and alerts household owners through a mobile app. So this is our GridAlert controller box, and this is the mobile app. GridAlert allows users to check power status in the home, switch on or off appliances plugged into its sockets, schedule appliance runtime, as well as visually check the amount of time they use electricity on each appliance. Correa et al. Explored various ways of improving blackout detection strategies using sensors. They found that increasing the number of sensors within a transformer increases power blackout detection. We implemented this strategy by deploying 3 GridAlert devices within each transformer. A blackout is detected when at least 2 of the devices detect blackouts at the same time. This helps to reduce detecting false blackouts, especially when users in one household manually switch off their devices. So as you see in these diagrams, a blackout is only detected if at least 2 of the households detect a blackout at the same time. We worked with local collaborators to design GridAlert's form factor. These included carpenters, painters, and electricians. We worked together with the carpenters to design the form factor using wooden plywood. After designing the boxes, we worked with painters to decorate the boxes with brown color. Carpenters chose this color because its furniture in most Kenyan homes is made up of this color, so they thought it could match with other properties in the home. So this is one of the carpenters we worked with, and this is one of the painters. We then worked with electricians who helped with soldering electronic components. The electricians also fixed the system's circuit into the box. They also helped in translating the system's US-based voltage of 120 volts to Kenya's 240 volts. To do so, we used a step-up transformer. After designing the system, we conducted a study in Kisumu, Kenya. So Kisumu is a port lake city on western side of Kenya, close to Lake Victoria. We had 18 participants who participated in this study, and these were sampled using purposive sampling in order to get participants who have at least one smartphone in their home and they have access to grid electricity. We had a total of 8 women and 10 men in this study. This included business owners, employees, and farmers. Participants were grouped into 6 groups of 3 to practically implement the strategy specified for detecting blackouts. The study was conducted in 2 phases. In the first phase, we conducted some structured interviews and observations. to understand the tools and materials in participants' home, especially those that they use to monitor power blackouts. Then we deployed GridAlert for a period of 1 month, and during this period, we gave participants diaries to record their experiences. We also logged the data to detect frequency of use on daily basis. After 1 month, we return to participants' homes and conduct follow-up study. This consists of in-depth interviews, which helped us to learn how participants used GridAlert during the 4-week period. Data analysis began in the field with taking field notes and discussing them on daily basis among the research team. And then after the study, we transcribed the interviews, and we used open coding to identify the patterns in these interviews. And these were turned into themes as well as categories. And we also used affinity diagramming process to identify patterns in the diaries that we collected from participants. Our preliminary home visits before deploying GridAlert suggest that participants had different appliances in the home. These included radios, televisions, sound systems, refrigerators, and DVD players. These appliances were mostly located on the same location. There are also non-electrical materials in these locations. For example, here you have a TV, you have speakers, decoders, and sound systems. At the same location, you also have matchsticks, paper towels, and books. The most common power monitoring tools we found in participants' homes included digital meters and power surge protectors. Digital meters were only used to check the amount of electricity, as well as add credit whenever participants are run out of electricity credit. Only 6 participants had power surge protectors, and these were used to protect one appliances from voltage spikes, especially during episodes of power restoration. Participants mostly used the power surge protector to protect their refrigerator, so they called it the fridge guard. Participants told us that they experienced about 2 to 3 blackouts each week. These blackouts caused damage of electrical appliances. For example, one woman described that there was a day she forgot to switch off her TV. The TV was damaged due to a power restoration that came with high voltage. Participants used different strategies to learn about power blackouts and restorations in the home. Some participants used their appliances as notifiers. For example, some used a TV. If they're sitting in front of a TV and they suddenly notice that it goes off, they realize there is a power blackout. Other participants used auditory cues to learn about power restorations, especially those who lived near a men's mill. If they suddenly hear that there's a sound, then they would know that power is restored in their households. Other participants continuously switched on and off their appliances to learn about power blackouts and restoration. This graph suggests that GridAlert continued running in participants' homes throughout the period of the study. The average daily runtime of GridAlert was approximately 13 hours. Data logged also suggests a total of 46 blackouts from all the clusters we deployed GridAlert. In 4 clusters, participants faced 2 blackouts within the same day in their households. As you can see here, these are 2 blackouts, 2 blackouts, 2 blackouts. These blackouts ranged from 30 minutes to 4 hours, and 2.5 being the average length. Participants appreciated GridAlert's power blackout functionality because it allowed them to switch off other appliances in the home. When participants received a notification about power blackout, they also switched off other appliances that are not connected to GridAlert as long as they're at home. However, participants expressed concern that they could not switch off the appliances even if they get the notification when they are far away from home. Participants also compared GridAlert's ability to protect appliances with power surge protectors. They said that GridAlert app gave them more control than their power surge protectors, which had no graphical user interface. Further, participants expressed that GridAlert gave them more control to also monitor their appliance as well as save time. Participants who owned electricity-dependent businesses, for example, barbershop and internet cafes in town, mentioned that when there is a blackout, they close down the shop due to the blackout and go home. So the home was about maybe 5 kilometers from where they're staying, from where they have their shops. However, they didn't have any criteria of learning whether power is restored in their shops. GridAlert allowed them to instantly learn about power restorations. This allowed them to go back and reopen their shops faster than without knowing when power is going to come back. GridAlert did not only allow participants to monitor power blackouts, it also supported participants' interest to save energy in their households. This, for example, these graphs that you are seeing here shows a 4-week energy use in a participant's home. This participant was checking his graphs on a weekly basis, and he learned that his security light was running more than the time that he actually uses it. With GridAlert, he started scheduling when it should go on and off. That dramatically reduced the amount of time the socket was running, thereby saving more energy and also preserving the energy so that other people can use it. Further, it was beyond our expectations that participants could use GridAlert for other activities in the home. It was interesting to learn that participants who had kids used GridAlert to monitor the amount of time their children spend on TV. These participants complained that their children spend more time on TV instead of doing homework or chores, especially when parents are away from home. GridAlert turned into a technology probe, revealing how participants wanted to use sensors to control their children's activities in the home. One of the participants said that he could switch off the TV from wherever he was whenever he's seeing that his children are using the TV for a long time than what he expects. GridAlert wooden box sparked mixed reactions among participants. While other participants liked GridAlert's form factor because it reminded them of their old wooden sound systems, younger participants, especially ladies, described it as not attractive. These participants expressed that they prefer plastic materials made in the US or China. However, they continued using GridAlert because its functionality was modern. These stories are useful for motivating new design concepts in HCI. The reactions about GridAlert's form factor questions whether it is important to continue encouraging using locally made materials for designing systems in Kenyan context. While various researchers have encouraged this, we propose further research on this topic. Participants' concerns about failure to manually turn off appliances when they are far away from home suggest a need to design whole household power monitoring systems. Further, instead of designing new systems, we suggest upgrading already existing tools in Kenyan households to consist of power monitoring functionalities. For example, just upgrading the power surge protectors, which doesn't have graphical user interface at this time. Finally, we propose designing research products in an open-ended way to allow participants' engagement with them. This research was sponsored by National Science Foundation. We thank Dr. Stephen Kimani, Dr. Augustine Wasonga, Cyril Amanya, and Martha Atieno for their help with this project. Thank you.